Hey Red Devil Chemists, how you doing? It's Coach Scott. Let's go ahead and work on some more homework sheets. We're continuing with homework sheet 6S, which is the gas law summary. So let's look at this problem. Calculate the molar volume of 1 mole of an ideal gas at 1 atmosphere and 25 degrees C. So what we're really trying to find is the molar volume, right? Which we know is 22.4 liters. This is asking us to prove it. So we've got what? Pressure is 1 atmosphere. 1 atmosphere. All right. Volume, we don't know. We're trying to figure out the volume. All right. Temperature is 25 degrees C. We've got to have it in K, 273. That's going to be 298 K. All right. And the number of moles, N, is equal 1 mole of gas. 1 mole of gas. So the formula we're going to use is P equals V, excuse me, PV equal nRT. So if I'm going to find volume, I'm going to go ahead and manipulate the pressure around. I'm going to have nRT over P. So now let's start subbing in. So my volume is going to equal 1 mole. 1 mole. All right. Pressure is 1 atmosphere. That means I'm going to use 0.0821 atmospheres liters over mole K. That's my unit. And if I actually wanted to really do that, I could show you that we could substitute the units out, and that would give me I would end up with liters, and that's why we use that. And then our temperature is 298 K. All right, 298 K. So we're ready to do our math. Let's turn on our math device, our calculator. So in order to get this, let's figure it out. 1 times 0.0821 times 298 divided by 1 is going to give me, look, 24.454658, all that. But essentially what it's going to give me is 24.4, 24.5, 24.46 liters. So volume of 1 mole of gas at standard temperature and pressure is this. 24.4, what did it say? 24.46 liters of gas. Now, depending on who you talk to, all right, standard temperature might be 0 degrees C. And if we were to do that, let's see what that would work out to. All right, so 1 times 0.0821 times 273 for 0 degrees C divided by 1 is going to equal 22.4 liters. And so that's where we get a little discrepancy, because we were using 0 degrees C. Our book uses 0 degrees C for standard temperature and pressure. All right. So that's going to be 22.4 liters. So again, we're right in there in that same molar volume. So that's one down. Let's go look at another one. All right, rewrite the ideal gas law equation to make molar mass the subject of the equation. Okay. So we know that the molar, or the ideal gas law, is PV equal nRT. So what does moles equal? Moles equal mass over the molar mass. All right. If I've got a mass and I'm trying to find the number of moles, all right, I've got a mass, I'm trying to find the number of moles. then I'm going to divide by the molar mass, right? So we can make this like this. PV equal N mass over molar mass. Let's go and make that molar mass RT. That's legal. So now we've got to solve for molar mass, right? Molar mass. So to solve for molar mass, okay, I'm going to call that MM. We know what that means. I'm solving for MM. So if I'm going to, if I would take MM and I multiply by MM, that's going to mean pressure and volume equals, and I'm going to put my MM here. I'm going to multiply by MM, my unknown, all right, equal mass times R times T. Now, if I divide through by pressure and volume on both sides, then I'm going to have molar mass, let's use the pink, MM, is going to equal mass times the universal gas constant R times the temperature in K divided by pressure and divided by volume. All right, and essentially that's all that question is asking for. It wants to make sure you understand that you can change things around a little bit. Okay, the ideal gas law around using a little algebra, and it's going to give you what you need, right? So I could, if I'm given mass, and I'm giving temperature, and I'm giving pressure, and I'm giving volume, I can find the molar mass of a gas by just rearranging the ideal gas law around. I think we've got time for one more before we need to cut off. Right. Write an equation for a mixture of three gases, A, B, and C, in terms of the partial pressures of the gases. So what I'm going to do is use Dalton's law, which is the total pressure of a system, of a gaseous system, is going to be equal to the partial pressure of the first gas. That's what that would be. Plus the pressure of the second gas. Plus the pressure of the third gas. So if I find the pressures of those three gases, I add them together, that's going to give me the total pressure of the system, of the gaseous system, if I've got a mixture of those gases. So we got that one done. Write an equation for the total pressure of the mixture of these gases in terms of the total number of moles of gas. The total number of moles of gas. So if I know the moles of A, and I know the moles of B, and I know the moles of C, and I add them all up, then I can put that into PV equal N RT, okay, and I can get the pressure of the system. So let's go ahead and do our little math stuff. I divide through by V on both sides, all right? And if I was to add the moles of all those gases up, I'm going to come up with this. Cancel that out. Pressure equals the sum of the moles, so we'll say the total moles, times R, the universal gas constant, times the temperature of the system. And if I divide through by the volume, that's going to give me the pressure. So again, thinking about throwing these gas laws together, using a little logic, you're going to get the answers to these problems. All right. Now I can use that if I know the total number of moles, and think about what's happening. All right. You're adding those little particles into that container, and those particles are moving independently of each other and crashing against that surface of that vessel. And whenever it crashes against that surface, it's imparting pressure. All right. So the more moles I have, the greater the pressure. Okay. So guys, this is Coach Scott. We've got one more to do on 6S, and that's pretty much a doozy. So when we come back, we'll do question 11, and that'll be all the 6S homework problems and I think you'll be okay with that. Okay, guys, this is Coach Scott saying peace out.